Right. As part of our equilibrium work, we're now going to explore something referred to as Le Chatelier's principle. Now, before we get there, let's take a brief look again at what the notion of equilibrium is all about. Here we have two diagrams. Um, the diagram above is a very nice visualization of the idea that when we talk about equilibrium, it does not mean things are equal. You'll notice that the large object on the left is a very large amount of material there. That's the big box. And the object on the right, there's a small amount of material. And so the amount of material on the two sides of this teeter-totter is not the same. Now, what keeps it at equilibrium is the fact that in this case the fulcrum is shifted far to the left. So what we have here is an unequal amount of items on the two sides, but the overall setup is at equilibrium because the equilibrium point is offset to one side. Now, there is a corollary to this idea when it comes to chemical reactions. You'll notice on the diagrams below, on the left, that the reaction, the amount of product, very quickly goes pretty high, meaning that the chemical reaction has been very successful in making product, and that the concentration of reactants drops very, very low. And so when you reach equilibrium, which is indicated by the lines going flat, no more change in concentration, there's a very high product production, and the amount of reactants left over, of course, is very small. Now, not all reactions work like that. If you take a look below, on the right, you'll notice that the amount of product being produced is actually relatively small, that the ratio of product to leftover reactant, it is really favoring reactants. We would say that in this case, this reaction is not very favorable because the amount of product produced is very low. But either way, you'll notice that the concentration of reactants versus product is not the same, even though equilibrium has been reached, meaning that the forward and the back reactions are continuing to go on at an equal rate. The actual amounts don't change, and the actual amounts are not the same on either side. Now here we take a look at mathematically what exactly this means. K is representing the ratio of the product over the reactant. And again, the amount of product and amount of reactant is not going to necessarily be the same. In fact, most often it's not. And so you can see how we have substance A and substance B producing substance C and D, and that you have now set up a product over reaction uh, um, situation. What is the consequence of this? Take a look down below. Notice that when the K value is much, much less than 1, it means that you have lots of reactants still and very low product when equilibrium has been reached. In other words, when the reaction no longer continues. And of course, K equals 1. At equilibrium, the concentrations are the same, and the K value is greater than 1. It means you have a lot of product. Now, why review all this? Well, the question we should ask is it possible to make a reaction that's at equilibrium shift? Can we make it so that there's more product made than before? In other words, we want to shift the equilibrium. And what Le Chatelier did was he figured out the properties or conditions that would do just that. And that's, of course, Le Chatelier's principle. And his basic idea is that if you apply external stress, certain external stresses to a system at equilibrium, that the amount of product and reactant will shift, and that the equilibrium will shift in an effort to offset or reduce the amount of stress on that system. It will produce a new equilibrium position. And there's Le Chatelier who figured this out. So here's how it works. What are the conditions that can be shifted, and produce a change in the equilibrium point? The answer is you can change the concentration of the reactants, and that, or products, by the way, if you add products from the outside, and you can shift the equilibrium by doing so. If you change for a gaseous reaction, for example, methane gas reacting with oxygen gas, if you were to change the pressure of the environment, you can cause a shift in the equilibrium. There's a catch, though. The direction that the equilibrium will shift depends upon the ratio of the gaseous reactants and products. And so we'll talk about that when it comes up. But to make that shift happen, certain conditions have to be met. Now, volume, yes, it will shift equilibrium, but you got to think here. The volume itself, changing the volume itself is not the issue. It's not because there's now more or less surface walls available. Rather, the volume produces a change in pressure, and now the rules of pressure change. And so the volume is directly associated with the pressure change. Temperature. If you change the temperature, yes, you can shift the equilibrium point. Finally, if you add a catalyst, interesting enough, a catalyst will not shift the equilibrium point. And why that is true, we're going to take a look at in detail. So let's explore concentration, pressure, volume, temperature, and catalyst. Let's explore the details of that. And again, this is all part of the Chaliers Principal, which is to say, can I shift the equilibrium of a reaction? So, concentration. The system will always shift away from the added material. So if we have this universal chemical reaction, if we change the or add the more product from the outside, you will shift the direction of equilibrium to the left. So increase the concentration on the right, and the equilibrium will shift left. If you now remove the product as it's being made, you will drive the reaction to the right. If you add more reactants to the system, you will shift it right. And if you remove items of reactants, you shift it to the left. And so these changes to concentrations would produce these kinds of shift in equilibrium. Now, how about pressure? Now, it's important to recognize that the reaction itself must be taking place in a gaseous state. So if we have now the N2 molecules, which are the large blue molecules, and 3H2, which are the small lighter colored, if we add N2 gas to this, then what's going to happen, is we're going to drive the reaction to the right. And the reason we do so is because it's effectively increasing the concentration and also increasing the pressure. Now, if you decrease the volume during that reaction, notice decreasing the volume itself is not the issue. It's if you decrease the volume, you increase the pressure. And when you increase the pressure, you can cause the system to change. So what's the volume and pressure issue? Notice they're all gaseous. If you change volume, you will change pressures. Increase the pressure, you will shift that to the side that has the fewest molecules. So for example, in the reaction given, there is substance A, substance B produces substance C. We will assume that the coefficients are 1, 1, and 1. So the number of moles of reactants is 2, because I have an A and I have a B. So I have 2 moles on the left, and I have 1 mole of C. So the rule states that if you increase the pressure, you will shift it to the side that has fewer moles. Therefore, in this case, increasing the pressure will shift it to the right. Of course, if you decrease the pressure, it will shift with the one that has most of the moles of gas, which in this case would mean shift it to the left. If you increase the volume, remember volume itself doesn't have much of an effect, but if I increase volume, I'm going to decrease the pressure. And if you decrease the pressure, the side with the most moles is where it will shift to. The best strategy I suggest is always think when you see volume, figure out the effect of pressure and then run your changes from there. Decrease the volume, you're going to increase the pressure, and it'll go to the right. So you have to realize that when you are changing pressure, you have to change it using the reactant gas. What we mean by that is, in this reaction, AB produces C. If you change the pressure by adding substance X, even though the pressure went up, there's no effect because you have to increase the pressure or decrease the pressure by changing the reactants. What about temperature? What happens here with temperature? It actually affects the equilibrium positions and the KEQ. Now, temperature is an increase or decrease in the amount of heat energy going into the system. So when the temperature goes up, it means you added heat energy. So the delta H is going to go up. And if, of course, you're cooling down the system, if the temperature is dropping, then what's happening is this system is losing heat energy. So you work with the energy or going in like a flame heating up a system or ice cooling a system. You work with it like it was an actual item that was involved in the reaction. So here we see that the N2O4 gas goes to 2NO2. Now notice that the delta H for the reaction is 58. Notice that a positive 58. Therefore, what this implies is heat is being added to the system. So you'll notice we can actually represent the reaction as N2O4 plus H naught, delta H naught, producing 2NO3. How did we know it belonged on the reactant side? And the answer is, in a chemical reaction, if in fact the delta H value is a positive, it means that it had to be added to the system, so it's viewed simply as a reactant. So the temperature is going to go up here because you added the heat, which you can see right there. And the result is you're going to drive the reaction to the right because you've increased the amount of reactant, in this case heat. When you do that, drive the reaction to the right, then the N2O4 amount will go down and the NO2 amount will go up. Now, if the temperature is dropping, what that means is you're lowering the amount of delta H naught. And when you lower the amount of reactant, then the overall reaction now shifts left. And you get an increase in the reactant and a decrease in the product. What's the take-home message here? Changes in temperature really mean that you're adding or taking away heat energy or delta H. And depending upon what side you put it on, you can figure out the direction it's going to go. Let's continue on this idea. Here's an illustration of how it works. We have on the left N2O4, it's in a gas vessel, and we have NO2 gas on the right. Now, if we make the system colder, it turns lighter because N2O4 is clear, NO2 is red. So when you make it colder, the reaction shifts to the left and it will become lighter. Now, if you make things hotter, then you're going to drive the reaction to the right. You're going to increase the amount of NO2 and the actual gas itself turns a darker red. And so this diagram nicely illustrates the effect of the direction or the side that is being favored in the reaction when you change the temperature. So if you have a delta H of reaction where there is no temperature change, then in fact the temperature has no bearing on it. What about catalysts? If you're adding a catalyst, you don't change K, you don't change the equilibrium. Well, why is that? Well, on the left diagram, you can see that the amount of potential energy A and B must create or must experience when they collide, you can see it rises up, and that's the activation energy, which is E naught A. Now, if you have a reaction where the EA is very, very high, then in fact you don't get as much product being made because you have to go over a very large amount of activation energy. Now, if you in fact add catalysts to a substance, you lower the EA. However, you are lowering it by the same amount going forward as you do going in reverse. So the result is, it's true, it's easier to go forward in the reaction, but you're making it equally easy to go backwards in the reaction. So the overall equilibrium point doesn't shift. Now let's take a look here, if we can, at a nice illustration of this.
Le Chatelier's principle states that if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset. The word stress means a change in concentration, pressure, volume, or temperature. Click on one of the buttons below to view animation showing the effect of these stresses on a Iron 3-thiocyanate, which is FeSCN3, dissolves readily in water to give a red solution. The red color is due to the presence of hydrated iron thiocyanate ions, FeSCN2+. The equilibrium between undissociated iron thiocyanate ions, iron 3+ ions, and thiocyanate ions SCN- is given by this chemical equation. FeSCN2+ aqueous, which is red, in equilibrium with iron 3+ ions, which are pale yellow, plus SCN- aqueous, which is colorless. Click on one of the buttons to add sodium thiocyanate or remove iron 3+ ions from the solution. In this case, the stress applied to the equilibrium system is an increase in the concentration of thiocyanate, SCN-, from the dissociation of sodium thiocyanate. To offset this stress, some iron 3+ ions react with some of the added thiocyanate ions, and the system shifts from right to left to re-establish equilibrium. When the system shifts to the left, iron thiocyanate ions are produced, which have a red color. Consequently, the red color of the solution deepens as more iron thiocyanate ions, FeSCN2+, are produced. Note that the sodium ions are not shown in the simulation because they are spectator ions. Consider the equilibrium between iodine gas molecules, I2, and iodine atoms at high temperature. Iodine molecules in the gas phase are a purple color, and iodine atoms are colorless. Under the given reaction conditions, the ratio of I2 molecules to iodine atoms is 2 to 3 at equilibrium, as shown in the microscopic view. Let's stress this system by changing the pressure. Click on one of the pressure buttons. You have decreased the pressure by increasing the volume of the container. Le Chatelier's principle states that this stress will be partially offset. The system can partially offset this stress by increasing the moles of gas. Pressure is directly proportional to the moles of gas. Because of the 2-to-1 mole ratio in the balanced equation, more moles of gas can be produced if the system shifts to the right, producing more iodine atoms, as you can see in the microscopic view. As more iodine atoms, which is a colorless gas, are produced, the color of the equilibrium mixture lightens, as you can see in the macroscopic view. Note that the total number of gas particles has increased from 10 to 12. Consider the following reaction at equilibrium. N2O4 in equilibrium with nitrogen dioxide, NO2. Under the given reaction conditions, the ratio of N2O4 molecules to NO2 molecules is 2 to 3 at equilibrium, as shown in the microscopic view. Because NO2 is a brown gas, the equilibrium mixture has a brown color, as shown in the macroscopic view. Let's stress this system by changing the temperature. You have increased the temperature of the system by adding heat. The Chaliers Principal states that this stress will be partially offset. This reaction is endothermic, so you can think of heat as a reactant. Heat must be supplied to the reacting mixture. The system can partially remove the added heat by shifting to the right, producing more NO2 and decreasing N2O4, as you can see in the microscopic view. As more NO2, a brown gas, is produced, the color of the equilibrium mixture darkens, as you can see in the macroscopic view.
So, equilibrium does not always mean equal, but we can shift where the equilibrium point is according to Le Chatelier's principle.